The objective of this video is to outline some of the basics of probability. We'll talk about some basic terminology, introduce some basic concepts, and carry out some basic calculations. Let's start with some terminology. When discussing probability, we talk a lot about experiments. In other words, procedures or trials whose result is uncertain. An example of an experiment is rolling a six-sided die. At the end of an experiment, we observe an outcome. When the experiment involves rolling a six-sided die, possible outcomes include 3 or 4. The set of all possible outcomes for a given experiment is called the sample space. It's often denoted using the Greek letter omega, possibly because omega is the end of the Greek alphabet and an outcome represents the end of an experiment. Regardless of the rationale for the notation, for the experiment in which we roll a die, omega contains the outcomes 1 to 6, as shown here. In discussions of probability, we often find ourselves focused on a particular event, which is a term that simply refers to any subset of omega. For example, 3 is an event associated with rolling a die by virtue of the fact that it's an element of the set omega. Another example is the event where we roll an even number. That's the subset 2, 4, 6. Perhaps less obvious is the fact that the entire sample space can be considered an event because omega is a subset of itself. The empty set, that is, the set that contains no elements, is also an event because technically it's considered to be a subset of any set. It's important to recognize that we can use events to generate other events. For instance, given an event E, we can create a new event EC, which is called the complement of E. The complement of E contains all outcomes in omega that are not contained in E. So, for example, the complement of the event 2, 4, 6 is the event 1, 3, 5. Given any two events, say E and F, we can define another new event called E union F, which consists of all outcomes that occur in E, or in F, or both. As an example here, if we take the union of the event 2 and the event 1, 3, we get the new event 1, 2, 3. Finally, we can take two events E and F and construct something called the intersection of E and F. This new event only includes outcomes that appear in both E and F respectively. If we take the intersection of events 1, 2 and 2, 3, we end up with a new event that consists of the single outcome common to both. I'll add here that sometimes two events have no elements in common, and in that case their intersection is the empty set. The next piece of information is meant to bridge our introduction to basic terminology with the introduction to basic concepts. In order to quantify the likelihood of a particular event, we talk about the probability of that event. We can think of probability, denoted by this funky-looking p, as a function that takes events as input, then outputs some number between 0 and 1. While this can happen in a number of different ways, we can always be sure that the probability of the empty set is 0, and the probability of the entire sample space is 1. It can be helpful to imagine the probability as an area. If we lay out the sample space omega as a rectangle, then we could say that the area of that rectangle is 1, corresponding to the fact that p of omega takes this same value. Sticking with the area analogy for the moment, we could also represent some event E as a region within omega. The area of that region, here denoted as an ellipse, would correspond to the probability of E. Moving on, for the case in which all outcomes of a given experiment are equally likely, we have a simple way of computing the probability of an event. To get the probability of E in this special case, we simply take the number of outcomes in E and divide it by the total number of outcomes in omega. When our experiment consists of rolling a fair die, then this formula applies. What's more, it's consistent with our area interpretation when we afford equal area to each of the possible outcomes. To tie up this point, note that we can compute the probability of getting an even number when we roll a fair die by simply noting that there are 3 equally likely outcomes in the event of interest, and 6 equally likely outcomes in the entire sample space. Based on the formula then, the probability of E is 3 over 6, or 1/2. This answer, of course, matches the fact that half of the area in the rectangle is taken up by even numbers. Perhaps that's obvious to you, but I think it's a nice check. When applying the formula we just encountered, there's one common pitfall you should be aware of, and I want to highlight that pitfall with an example. The example is this. We'll roll 2 fair dice and sum the numbers showing on their faces. With this experiment in mind, one might be inclined to declare omega as the set that includes the 11 integers from 2 to 12. And there's nothing really wrong with that, but when we lay things out this way and then are asked for the probability of getting a 12 or the probability of getting a 7, we might look at omega and decide that the answer in both cases is 1 over 11, which is wrong. In this case, we've fallen prey to lazy thinking. Just because we can count the outcomes in omega doesn't mean they're equally likely to occur. And if they're not equally likely to occur, then our previous formula is useless. A better approach involves presenting the results of the experiment in a way that lays bare exactly what the equally likely outcomes are. In this example, we can do this by listing the equally likely outcomes associated with rolling the first die, die A, then doing the same for the second die, die B. For both die A and die B, the equally likely outcomes are the numbers 1 to 6. And as the table here suggests, there are actually 36 equally likely outcomes for the experiment as a whole. We could roll a pair of 1s, for example, in which case we get a total of 2. We might also roll a 1 and a 2 to get a 3, or a 2 and a 1 to get a 3. Continuing like this, we can fill out the entire table and ultimately realize that the probability of getting a 12 is 1 over 36, while the probability of getting a 7 is 6 over 36, or 1/6. Just to summarize here, with elementary problems like this, it's helpful to think about equally likely outcomes, but it's absolutely necessary when you're relying on calculating formulas that assume this fact. There's another calculating formula you need to know about. This one applies to all experiments, even those whose outcomes are not equally likely. The formula tells us that the probability of the union of two events is equal to the sum of the probabilities of the individual events minus the probability of their intersection. Our area analogy can be used to help us understand where this formula comes from. Consider two events, E represented as this region, and F represented as this region. E intersect F would then be the event that corresponds to the overlap, as shown here. Now, we can represent the probability of E union F as the total area enclosed by these regions. Clearly, if we were to only calculate the area of E union F by adding the area of E to the area of F, we'd have incorrectly counted this area of overlap twice. So, to get the right total area, we need to subtract the extra copy of the overlapping area from the sum, which is why we have subtracted P E intersect F in the formula. To see an example of this formula in action, let's once again consider rolling a fair six-sided die. We'll ask for the probability of rolling a number that is either strictly less than 5 or even. So here we can think of E as the event rolling a number that is strictly less than 5, and F as the event rolling an even number. Using the fact that the basic outcomes of the experiment are equally likely, we can see that the probability of E, rolling a number that's strictly less than 5, is 4 over 6. There are 4 numbers on a die that are strictly less than 5, and there are 6 possible numbers we could have rolled. We've already seen that the probability of F, rolling an even number, is 1/2, or 3 over 6. And so it only remains to subtract the probability of rolling a number that is both strictly less than 5 and even. There are 2 such numbers, namely the number 2 and the number 4. And we still have 6 outcomes, so we end up subtracting 2 on 6. In the end, we see that the probability of the union of events in this case is 5 over 6. A quick check shows that we're spot on. 5 of the 6 possible outcomes of the experiment are either strictly less than 5 or even. Note that in the special case where E and F are what we call mutually exclusive events, the formula at the top of the screen simplify substantially. We say two events are mutually exclusive when their intersection is the empty set. Since the probability of the empty set is 0, we can say that the probability of the union of two mutually exclusive events is indeed just the sum of their individual probabilities. Again, this makes total sense from the area perspective. As an example, we could ask for the probability of rolling a number that is either strictly less than 3 or strictly greater than 4. These two events are mutually exclusive because no number can be simultaneously less than 3 and greater than 4. It follows that the probability of the event is simply the probability of rolling a number strictly less than 3, that's 2 over 6, plus the probability of rolling a number that's strictly greater than 4, that's also 2 over 6. Summing these probabilities gives us our answer, 2 over 3. Let's recap. In this video, we defined some of the basic terms used in probability. We outlined some of the mathematical properties associated with the probability of an event, and we introduced its area interpretation. We also saw how to calculate the probability of an event for experiments whose outcomes are equally likely, and we uncovered a formula for calculating the probability of the union of events in general. Once all this stuff is sunk in, you'll be able to define the various terms we encountered and identify the corresponding objects or constructions when presented with an example. You'll be able to state the properties of the probability of an event and discuss it using its area interpretation. You'll also be able to compute probabilities of events associated with experiments whose outcomes are equally likely, and you'll be able to apply the formula we encountered for the probability of the union of events to calculations in general. Remember, there's more to learning about probability than simply watching a video. Read the notes, try the assigned problems, and maybe even read again. Keep at it, and you likely won't need to roll the dice come exam time.